So, my name is Jonathan Tenenbaum. I'm going to present to you a refutation of the first and second laws of thermodynamics. Now, when you go to university and study physics or take a physics course, I never did that, fortunately, but if you do that, they will tell you that there are the laws of thermodynamics, particularly the first law, otherwise known as the conservation of energy, and a second law, sometimes known as the law of universal entropy or of the increase of entropy in any closed system. And these laws are the unshakable foundations of physics. And in fact, if you will go into a physics department and go to a physicist and tell him that, well, I'm sorry, but the law of conservation of energy is not true, then you will experience, and this has actually been, the experiment has been done several times, that the individual will usually go into a screaming fit and throw you out of his office. Generating a lot of energy. Departing very far from equilibrium, as they say now.
What does that mean?
Well, throws you out of the office. Now, and this suggests from the psychological phenomenon involved, which is actually can be very, very extreme, that the fanatical belief, in any case, in these laws is associated with a phenomenon which is clinically called psychosexual impotence. And I will, I think, demonstrate to you that in a rather rigorous way. Now, if we look at the actual physical evidence, that is what mankind has actually learned about how our universe works, then, and I will show this to you, we see that these two laws are actually not laws of nature. If we compare them to the evidence, I think we can only come to the conclusion that they must either be considered wrong or, at the very most, vacuous. That is to say, they apply essentially to no part of physical reality, or if they apply to any part of physical reality, is essentially 0.00000% of the universe, which obeys these laws. Or another way to say it is that they are essentially tautological or circular. That if you look at them very carefully, and you try to actually pin down their area of precise validity, insisting that they are universal laws, you will find that you get a statement like, the first law of thermodynamics is true for those systems which obey the first law. And if we look more carefully, and I think I will demonstrate this for you very clearly, the insistence upon the validity of these two laws, so-called laws, is essentially equivalent to insisting upon a specific form of presentation of science, or specific form of science, or mathematical physics, namely a logical deductive form. That is to say, what the professor is really defending, what he's really screaming about, is the implicit attack on a way of thinking, not on physics, at least not on the physics of the real universe, but on a way of thinking about the universe, essentially on a kind of religious belief. It's not articulated as a religious belief, it's actually a superstitious belief in the power of deductive logic. The idea that you can understand the universe by laying down a set of mathematical laws and deriving by logical deduction from them everything else. Now, there is a certain vicious circle involved in this, in the following sense, as I shall show to you, that every fundamental discovery or revolution in science, by implication, disproves these two laws. However, and in addition to this, in a certain sense, every fundamental breakthrough in science, scientific revolution, in a certain sense, increases the energy of the universe. The universe becomes more powerful, has more energy, each time a scientific revolution is made. The vicious circle is contained in the following, that if we insist upon a logical, deductive form of physics, then if we confine ourselves to that physics, we will not make a fundamental scientific revolution, and then we won't do those things whose implication is to increase the amount of energy in the universe. And therefore, to the extent that we insist upon the logical deductive system, for us, the universe then becomes, in fact, limited and entropic, because we're not doing the things which make it negentropic, or at least make our relationship to the negentropic universe negentropic. And so, in that case, our relationship to the negentropic, real negentropic universe becomes entropic, and we disappear. So, you can see from this that there's also political angle on it. And we can see that from a lot of the things that we hear as popularized implications of the laws of thermodynamics. So, for example, we have the doctrine of the limits to growth that say there's only so much energy, for example, coming from the sun or in the form of oil and gas and uranium and so forth. We're using it up. Now, since energy is conserved and we're using it up, finally we're going to come to an end. Limited resources. Also, Jeremy Rifkin wrote a book called Entropy, in which he said that the second law of thermodynamics shows that man is in fact increasing the entropy or disorder, to put it in a popularized form, of the world. And the more man is doing things, the more chaotic the world is becoming. And therefore, man should do as little as possible. Don't move much. Don't breathe too much, because you're actually hastening the demise of the universe. This actually goes back to Lord Kelvin and Helmholtz. You can find a similar thing in Kant. The idea of the heat death of the universe, that in fact, due to the second law of thermodynamics applied to the universe as a whole, that the universe is actually devolving. It is running down toward equilibrium. All the differences, all the differentiations are running down, just as when we put a tank, and in one part of the tank we have hot water, and in the other part of the tank we have cold water, and we remove the partition, and then you see that the temperatures are equalizing. By implication, Helmholtz said the universe is moving toward the heat death, that is toward thermodynamic equilibrium, where everything will have the same temperature, and then there will be no more possibility to do anything. It will be, as Hegel expressed it, a night where all cows are black. And this has been developed further, because obviously if we take this idea of the universal entropy, or the universe is continuously running down, then we have to understand how it could be possible for organized processes, such as living organisms, to exist in such a universe. And within the confines of fanatical belief in these two laws, some more or less clever people have invented the notion of the so-called dissipative system. This is due to Ilya Prigogine, the Nobel Prize winner, whose idea is that you have the universe is running down, but you still have some energy flows in the universe. So the living organisms are a kind of parasitical process, which is living off of these energy flows. Just like when you have a waterfall, there's some vortices there, and the vortices are like parasitical processes which are powered by the motion of the water. But when the water is all run out, then these parasites will disappear, And in fact, the existence of these parasites, of life, which is living off of the dissipation of energy, therefore they're called dissipative systems, is actually mediating the increase in entropy. Therefore, living processes, including man, according to this belief, is actually participating and furthering the death of the universe. And this is the oligarchical standpoint. It leads, of course, this standpoint leads, of course, turned around a different way to a notion of imperialism, because if we only have finite resources, if the things are running out, then to keep things going, you have to keep grabbing for more and more resources. This is all part of this same way of thinking. So therefore, we have an implication or a suspicion that maybe these first and second laws of thermodynamics, so-called laws of thermodynamics, are actually not laws that developed in the natural development of physics, but were actually imposed by political dictate from outside of science. They were an intervention into science. To the extent they are formulated in the sorts of ways I've indicated to you. These were imposed upon science from the outside. And in fact, closer historical examination of the origin of these two laws as they are commonly presented in the textbooks shows that this is in fact the case. This is true, that the setting up of thermodynamics in this form is essentially a political operation, very closely connected with Malthus, as the case of Lord Kelvin shows, but you can trace it back to the Bogle mills, or so-called buggers, many centuries ago, to Descartes, to Newton, and so forth. You can also make another interesting comparison. The first law, the conservation of energy, is actually equivalent to the Malthusian idea of the limited resources. The second law, the idea that entropy is increasing, is essentially equivalent to Marx's law of the falling rate of profit, by which the so-called capitalist economy, industrial economy, is doomed to finally run down, run out. And in fact, if we look earlier, we find, and I reference the Leibniz-Clark correspondence, the very famous exchange of letters between Leibniz and Clark, who was a follower of Newton, or may have been fronting for Newton personally in this exchange of letters, in which Leibniz makes a devastating critique of Newton's physics. Newton's physics, if you can read it in the Principia Mathematica of Newton, his great work, where he indicates that in his system of planets, that due to the tidal forces and so forth, that the planets are losing energy, and they're therefore, and also the stars are slowly losing energy, and they're getting closer together, and finally they will collapse into a big clump. And then he says God will have to intervene and pull apart, intervene to pull this mass of the universe apart. And he says the reason why the stars are so far apart, Newton says, this is literally true, is that God in his infinite wisdom decided to put the stars as far apart as possible to delay the collapse of the universe. And Leibniz very, very rightly said, well, Newton has a very, very strange notion of the Creator. Newton is saying that the Creator isn't a good watchmaker, because his watch, namely the universe, is continually running down, and he has to wind it up again. So in fact, as I will show, the form of physics of Newton, this logical deductive form of physics of Newton, essentially collapses every time a crucial change occurs in the universe. So it collapses, so to speak, at the crucial moment. And this correlates with the well-known problem that Newton had with women, which John Maynard Keynes refers to, of this collapsing, this physics that keeps collapsing on you. So, took you a long time to get that. So now what I want to do is I will first critically review the first and second laws of thermodynamics more or less from the standard textbook standpoint, presenting to you more or less what they are, not in every detail, but what the essence of it, as far as I can see, is from the standard textbook's point of view. And I will drive this to the limits. I will push the statement of these laws to the limits to reveal the assumptions which are built in, often not stated, but there are certain assumptions which are made in these laws, which I want to bring into full view so we can see what is assumed, and therefore what assumptions may have been slipped in between the lines of the fine print when you sign for your doctorate degree of physics, that something's been slipped in through these assumptions which weren't stated, which you're going to pay for later on. And then after that, I'm going to use the method outlined in LaRouche's latest essay on the subject of God to refute systematically the first and second laws, which is a very easy exercise and a very brief one, and demonstrate that we live in a universe whose fundamental law is neg-entropy. Neg-entropy. The universe is winding itself up continuously. It's not running down, but it's actually running up. And in which, in a certain sense, energy is constantly being created. So let's look first at the principle of so-called conservation of energy. Well, the basic premise of the whole thing is that we take some kind of a physical system, as they're called, and we try to associate to that system an energy value. Energy being commonly defined as the capacity to do work. Well, so for example, when we define kinetic energy, we have some moving object, and we try to see how much work we could do by slowing down that object. For example, if we attach to the object a rope and a pulley and have the moving object lift another object. Oop. Is there any chalk here? Seems there's no chalk. Somebody could get some, it would be useful. All right. We can, the way we measure this energy, or try to measure this energy, is we take some physical system. It can be a moving object. It can be it can be a chemical process, and so on and so forth. And in order to measure its energy content, we have to have it connected to some measuring device or some reference device which it does work on. So there are two things involved in this. Firstly, is involved already an assumption. The assumption is that we can actually isolate a physical system from its surroundings so that we can talk about the energy inside the system. In other words, that we can actually put a wall implicitly around the system and separate it from the outside, and thereby speak about the energy in the system. Well, it may be obvious to most people that you can do that, but it's an assumption. It's the assumption built into this idea that the universe and processes in the universe can be understood as interactions between systems. One interacting with another next to it, or influencing another next to it. Assuming, therefore, that we can break down the universe into parts in that way, or at least regions in that way. Now, in fact, already the so-called quantum phenomenon, the so-called wave properties of particles, show you already that that assumption is not so self-evident as you might think. If we take an electron, in the standard version of physics, as physicists now view them, we take an electron and we put a box around the electron, we have fundamentally changed the electron. The electron is in a completely different state when you put it inside a box than when it's not, when it's a free electron. It has all kinds of when you put it in a limited box, suddenly the electron only has a certain discrete set of states, which it doesn't have when it's free. If you know a little bit about the so-called quantum physics, and you'll see that in fact, once you put the electron in the box, you still haven't isolated it, because you'll find that every process anywhere in the universe will be correlated with that electron. In fact, sometimes you'll find the electron outside the box. This is the textbook physics thing. So textbook physics is a little bit contradictory on this question of whether you really can say this system is now interacting with this system, because each system is actually everywhere. Okay, but let's be generous and let's leave out these kinds of problems. Let's suppose that that's not the case, but that we really can speak of isolatable systems. We can say we'll take this part of it and divide it up and look at how the different parts are interacting. So how do we do this? Still no chalk. If that's easier than finding some chalk, then this is like in the Soviet Union, though. If there's a screw missing from your car, you get another card. It's true. They had, at a certain point, they had 3 times as many combines in agriculture than the number that were actually working. Because the combine would generally, first it would arrive and it wouldn't work. They'd try to repair it, and you just kept waiting for the repair parts, which never came. So at the same time, you order a new combine and hope that the new one will have all the parts there. But in fact, especially in the last 5 years in the Soviet Union, during the transport of the combines on the railway, they were looted by farmers who were looking for spare parts. So the new combine, which you had ordered for your cooperative farm, arrives as a skeleton. Well, look at this. It's very frustrating. The productivity is actually very low, especially when harvest time comes and there's no seed. The seed doesn't arrive, but you have your quota for planting. So you put sawdust in the planting machine and run through and plant sawdust. And then when the harvest time comes, the harvest people have their quota of the number of acres which they have to harvest. They run over first, they put the fertilizer on, and then they run over and harvest nothing. Okay. Entropic system. Okay. So let's it's better. Okay. Fine. So let's do the energy game. In the energy game, you have to, in order to define energy, you have to define a reference system, which you use as a measuring rod for every other system. So it could, for example, be a big weight, which can be lifted up and down, and the level of the weight is your measure for how much work is being done. So you could, this could be your reference system. Here's something coming in, and you have a weight in there, and a dial which shows you the level of the weight. Okay. So for example, you could measure, if you have a spring which is compressed, or let's say if you have a moving body which is moving, and you want to measure its energy, you attach it by some kind of a device here with pulleys here and here and here. You attach it, okay, and you allow this moving body to lift the weight. And when it's finally stopped, you look and see how far the weight has been lifted. This kind of idea. This defines the energy of the moving body. Or if you have a spring which is stretched, you could attach a spring the spring here and let the spring compress, and as it compresses, it lifts the thing, and you can say, okay, well, the spring had so and so much potential energy being stretched. So this is, to simplify it very much, what you do is you have your measuring system, your reference system. And you have any other physical system, some black box system S, and somehow you hook it up with your reference system by some kind of an interaction. And you try to see how much work your system can do on the reference system. And you go around, you measure everything this way. All right, so that's what you in fact do. That's how this idea of energy is introduced. It's a system of accounting, essentially, the way it's done. And we try to associate now by this to every physical system, every state of the physical system. As the system is doing work, it changes its state, such as the moving object becomes slower or faster. So we have a relationship between the state of the system and the amount of work it's doing, so that we can measure when the system goes from one state to another state while it's working on the reference system, that it does so and so much work in terms of how far the thing is lifted. And by this, we try to associate to each state of a physical system an energy value. And we go around all physical systems and we start to do that. We assign numbers. Now the problem with this is, how do we know that this is a consistent thing, that we don't have a physical system in a certain state, we assign at one time one energy to it, and then somebody else, starting with the same reference system, but doing everything in a different order, comes back to the system and has a different energy value. How do we know that we're consistent? Well, this is in textbook physics proved by the fundamental assumption that there is no such thing as a perpetuum mobile, no such thing as a perpetual motion machine. A perpetual motion machine, well, this is a very subtle point. A perpetuum mobile would be some kind of a physical system which keeps doing more and more work. Well, I will assert, and I believe prove to you, that such a thing does exist, in fact. But it's not a machine. A perpetual motion machine would be, in fact, something very, very strange. The strict, rigorous, from the standpoint of textbook physics, definition of a perpetual motion machine is a physical system which goes through a cycle and returns exactly to its original state, and in the meantime has done work on the outside, say on the reference system. And therefore you can have it do another cycle, because it's returned to its original state, and it keeps going through this cycle and doing work without changing itself. Well, that would be, in fact, a very absurd thing, because it would essentially imply that there's no causality in the universe. That you could have something which changes something else but is not changed itself. That would be absurd. And so, as intelligent people, including Leonardo da Vinci and others, criticize those who over the centuries have tried to make such a perpetual motion machine and said it's absurd. It's in contradiction to the idea of a lawful universe. Something which moves but's not moved, well, that could be God, but God is not a machine. And God never returns to his original state. So there's no perpetual motion machine. What does that mean then in our assignment of energy to different systems? Well, it means that we're not going to come to any inconsistency as long as we assume that the way in which these different systems are interacting with each other is according to fixed qualities of interaction. Because if we're doing this process of allowing our system to operate on the outside, and the system is constantly changing the way it's interacting with our reference system, then we have a problem, because we never actually come back, we never actually go through a cycle. Well, I'll demonstrate the problem with that. That we have made, in assuming the conservation of energy, in this way of measuring things, two axiomatic assumptions. Firstly, we've assumed that physical processes are reducible or analyzable in terms of interaction between isolatable systems. Secondly, we've assumed, to the extent that we believe we can apply these measurements, that the systems have a fixed quality of interaction. In other words, that if I allow my system to interact with my reference system in one way and have it interact in another way, then I'm going to get the same answer. That would be true if I could get my system to go back to its original state. But if I have a system which evolves, I never actually get back to the original state. Well, what this suggests is that in fact the first law of thermodynamics is nothing but a bookkeeping process. It bears this way of assigning energy or energy content to systems is the same thing. Its relationship to the real universe is exactly the same as the relationship of money to an economy. So those who say, for example, there are many people who believe this, that your economy is limited in growth because you only have a finite amount of money. You can't grow any further because you only have so and so much money. So Adam was given by God at the very beginning of humanity a certain amount of cash. And that's it, you know. Well, to make this very more clear, now that we've sort of at least sniffed something very restrictive in the assumptions behind this thing, let's see what happens when there's a change in the way in which the system you're measuring is acting on the reference system. Let's take the following situation. Let's take some rock or some object that we found, and let's say, what is the energy of this object? What is the total energy of this object? Well, if we are caveman, we say, well, this object is a bit above the ground, so if I let it fall, I could lift something. Well, actually, a caveman doesn't have a pulley, but maybe a lever. So the caveman could say, okay, if I let it fall, or if I push a rock off of a mountain, then I can get a certain amount of work out of it. Okay. So the caveman will measure, will give you a certain number. He'll say, here's your rock. Here's your rock up on the mountain. Okay. And the caveman says, I can get so and so much energy out of just letting it roll down. So he writes down a certain number, whatever it is. Energy. Energy, caveman. Okay. And no matter what the caveman does that he knows how to do, he can never get more out of it. Now let's suppose that we come around later on, after fire has been discovered, and it turns out that this object is a pure metal, and it can be oxidized. In fact, it burns. A pure metal like sodium will burn. Yeah? Maybe it's a sodium rock, a pure sodium rock. That would be quite a find for the caveman. If it's a piece of sodium, then exposed to the air, it will burn. And if we took that energy, which we could have used to run a steam engine, we would get much more out than, depending on how high the mountain is, than what the caveman thought. Or we first let it go down, and then here we burn it and get more out from our steam engine. So when you go later, you find out this was not a correct value. But in fact, you have to add the burning. Okay? Or we could say for this purpose, we could start with a log or a piece of wood. Before you know how to burn it, you can only let it drop. After you know how to burn it, you can let it drop and burn it. Okay. Now we go later on, and if we keep it within that technological level, we can assign energy values in a consistent way. Yeah? Everything's fine until somebody discovers that the rock is uranium. And then we say, well, we can put this thing in a reactor, and we get approximately 1 million times more than we had. So we had a slight mistake in the assignment of energy by a factor of 1 million. Well, this is all a question of how the system is allowed to interact with our measuring system, right? Under what process are we allowing the system to act upon our measuring system? Well, so that means that at no point can we actually assign a number and say this is what there is, because we don't know if later, by a change in the characteristics of action, we uncover a new dimension of physical action under which there seems to be more energy in the system than before. So the implication of this is that the so-called energy value is not an absolute value, but depends upon our physics. And it develops with scientific progress. Well, now somebody's going to come up with a clever objection to that. They can say, yeah, but Einstein proved E equals mc squared. That the total energy contained in the system is equal to the mass of the system times the square of the velocity. Which means that, for example, when I use my uranium to generate nuclear energy, that the mass, the weight of the fuel after you've burned the fuel in your reactor will be less than what it was before by an amount which coincides exactly with, or fairly closely exactly with, what is predicted by Einstein's equation. So then the physicists will say, well, okay, so once you've converted all the mass to energy, the system isn't there anymore. Of course, we can't do that with a nuclear reactor, but there's so-called matter-antimatter reactions, which supposedly annihilate matter and transform it into pure energy, whatever that means. So this looks like a complete limitation. So if we were to start with the Earth, and we're limited to the Earth, and we are devising all kinds of clever devices to produce energy with what we have in the Earth, finally you'll get to converting the mass of the Earth into energy until the Earth is all used up. Right? There's only a slight problem with this, if we're critical. What is this mass? How is it measured? Well, you have to have an interaction. When you measure mass the same way you measure energy, you have to have a reference system. And to measure mass, you have to weigh something, which is an interaction, or you have to try to accelerate something. But in each case, the measurement of mass is associated with a certain physical interaction. What you measure is never a thing or a property, but always a physical change. So therefore, when you have different types of physical change, you get different results. Now, most of us would never imagine that the mass of something could ever change. But if you think about it carefully, it's the same problem as with energy. And I can predict for you with great peace of mind that we will find that the mass is changing in such a way that this relationship will be determined to not be correct. Because it's the same kind of problem. If, for example, the mass of an object depends on where it is in space or some other characteristic of it, by some very small change, which we can't measure at the present, then we're going to find that mass is not a fixed property or something. You get different masses depending on how you measure it. Well, by the way, there was a well, I won't go into that. It'll confuse you a little too much. Okay, so now somebody will come to me and say, yeah, this is your example with the rock falling and then it burning and then it generating nuclear energy. Oh, that's impressive, but what is the next step going to be? How do you know that there is a next step? How do you know that we're not at the end of this? And I say, well, that's exactly the vicious circle. What you're saying is that in order to defend the idea of the conservation of energy, you're saying that there won't be any more scientific revolutions. And then you're right. Because if you don't have any more scientific revolutions, you will never change the way that you're acting upon the universe. You'll never change the characteristics of action, and then therefore it will seem that you're back in a situation of conservation. Well, there's a deeper level to this. Because the person will say, well, all right, I can't prove isn't an end that we already know everything more or less that we're going to find, but how can you prove that it's going to go further? Since obviously discovery is a random process. Wait a minute. If I can show that this process of scientific progress has a law, is a principle by which mankind continually makes scientific revolutions, then I know that the law of the universe is the increase, implies an increase in energy. Discovery is not a random process, but a lawful process. Okay, well, let me go further. Let's go to the second law. What is this? The second law was derived from, historically, from the alleged impossibility of a so-called perpetual motion machine of the second kind. This was developed in particular by Lord Kelvin, William Thomson, otherwise known as Lord Kelvin. The way he got this is he took the work of Sadi Carnot, the son of Lazare Carnot, on the steam engine, and he set about to develop a logical deductive form of thermodynamics, starting with Carnot's analysis of the steam engine, which was a competent analysis of the steam engine. And generally speaking, the heat-powered machine, a machine which transforms what we call heat into what we call mechanical work. What Carnot observed is to have a steam engine, you have to have a difference in temperature. To actually get work out of a steam engine, you have to have something that you heat up, you have to have something that's hotter and something that's colder. In the classical Carnot cycle, he studied the way in which energy flowing from a source at a higher temperature to a lower temperature is doing work. And so that in a typical heat engine, you have to have a cooling. If you would have your steam engine in a room where everything was of the same temperature as in a closed room, closed system, where everything was of the same temperature, you couldn't get the machine to work. So, because you could get, well, anyway, I should be clear enough. If you start everything at the temperature of steam, then the water's already boiled, so you can't get any expansion. To get the expansion, you have to first condense with something cooler, and then heat it to expand to get work out of it. So you have to have heat passing from higher temperature to lower temperature. So, therefore, this principle of the second law of thermodynamics was considered, could be formulated axiomatically as a consequence of this principle that it's impossible to extract mechanical work within a system at uniform temperature throughout. So I could have an object whatever system it is. And although, let's suppose it's in so-called thermodynamic equilibrium, which means everywhere the temperature is the same, then although the system has energy, at least the physicists believe it has because the molecules are moving, so there's energy there, but I can't extract any energy unless I have another system at a lower temperature. Then I can extract energy by allowing the heat to flow from one to the other. But just from this system alone, although it has energy, I can't get it to do any work. So that's the principle of the second law of thermodynamics, which can be expressed in various different ways. When you make a logical deductive system, you develop all kinds of theorems out of that. And you can define a parameter called entropy, which I won't go into how that's done, which measures the way in which systems converge naturally toward thermodynamic equilibrium, such that, for example, if I have two systems at one temperature, another system at another temperature, and I put them in contact, the hotter body will get cooler and the cooler body will get hotter until they are at the same temperature. Thermodynamic equilibrium. And this is the idea that Helmholtz had of the heat death. That the universe will finally all become the same temperature. It will be all like a big mayonnaise. So this seems like an unbeatable principle. Have you ever seen heat flow from a colder body to a hotter body? Well, you can make it flow by doing work with the refrigerator, for example, but otherwise you can't. So what's wrong with this? What assumption have we made besides the assumption of the isolability of systems? Well, we're always talking about temperature. What is this temperature? How do we measure temperature? Well, we have to have a thermometer, which is a reference system. We put it in contact with our system, and we have our system do work on the thermometer. There has to be a transfer. There has to be an action, an interaction, in order to measure the temperature of anything. So now we have a problem. Let's take two pieces of uranium, pure enriched uranium-235. About 1 kilogram will do. Take the two pieces. And now, let's see. Now we put them together. They're each both at the same temperature. Put them together. There's thermodynamic equilibrium. Boom! Nuclear explosion. What happened? What was the temperature of the uranium? Or, let's put it this way. Was the uranium at thermodynamic equilibrium? Was it at equilibrium? Well, if it was at equilibrium, how come it suddenly explodes? Because when you're at equilibrium, you're supposedly dead. Nothing can happen. If the system is at equilibrium, nothing can happen. So I have my uranium. It's at a constant temperature, both pieces. I put them together, and boom, I have a nuclear explosion. Well, in fact, Marie Curie, at the time when radium was discovered, when she discovered radium, she posed this question, said there's something wrong. This is not supposed to happen according to the second law of thermodynamics. You have a system that's at a constant temperature, and yet it's continually doing work, in the sense from radiation coming out of it. Well, you could say, aha, yeah, right, that's true. We didn't quite, well, the problem was that our thermometer was too big to actually measure the heat of the nucleus, because nucleus are real hot, right? But they're closed up. So if I could take my thermometer and stick it into the nucleus, I would get a huge temperature. And that's what's liberated in the explosion. So in fact, it wasn't really at thermodynamic equilibrium, at thermal equilibrium. It only appeared to be so. But this is the same kind of cheating in a certain way as we were doing with energy, where you have one answer at one time, and later on you say, no, that wasn't the right value, it's another value. So that as physics progresses, you have to change what you said was the temperature of this system. And before you were saying it was in equilibrium, now you're saying it's not. So what is the case? What's the final answer? There isn't any. So when we set about to try to assign an when we say, okay, well, we have a law that says that entropy is always increasing. In a closed system, the entropy is always increasing, no matter what happens. Well, fine. Okay, what is the entropy of this system? Well, you have to go around measuring it. But then later on, you're going to say, no, that wasn't the right number. It's a different one. So we see a real fundamental problem. Now, Boltzmann and Maxwell tried to solve this question by developing the statistical thermodynamics. And saying, okay, well, let's get away from the steam engine and temperature and so forth, and let's reduce everything down to mechanics, to what we know about. We'll say that the universe consists of particles which interact according to some fixed laws. And let's derive thermodynamics from the statistical properties of systems of large numbers of particles. And this was the Boltzmann's famous H theorem, where Boltzmann mathematically defined a parameter called entropy for any system of particles and demonstrated that under actually rather strong mathematical assumptions about the way the interaction, about the law of interaction, that in fact the entropy does increase in all changes of the system when the system is left to itself. There's a little bit of a problem here, because Boltzmann, in order to do that, he has to define for a physical system what's called a phase space. In other words, he has to define a set of coordinates, a set of mathematical parameters, in ordinary, any machine in formal so-called analytical mechanics, we learn how to take any machine and define the so-called basic parameters of the machine, and then we can calculate with it. But there's an assumption involved, namely that what is called the degrees of freedom, the number of parameters we require to completely specify the system, that this is fixed and given. But what if we have a system where the phase space is changing, where new degrees of freedom are being opened up? Then we have a real problem, because we could start from a state of the system which seems to be very random. Suddenly we realize there's a new degree of freedom, and the system is actually only now in a very small part of the phase space. So it goes from having a high entropy to having a very low entropy. I'm speaking for those that know a little bit of the statistical mechanics. When an additional degree of freedom is introduced. Well, does that happen? Well, in a certain way, and this is the subtle point, and a very crucial point, what are we going to say? We take our uranium as an ordinary thermal system, disregarding the fact that the nuclei are about to do something terrible to us. It's in equilibrium. Now, has a certain entropy. Now, if we take into account the fact that the nuclei are not fixed objects, but there's incredible activity going on inside there, suddenly we're not in equilibrium, and suddenly we have all kinds of new parameters which we need to describe the system. It's not enough to say where each atom is. We have to say where each component of the nucleus is. So we have a lot of more degrees of freedom, a lot more things that can happen. Well, so that if we look generally now at the first and the second laws of thermodynamics, so-called laws, we find that they both depend upon assumptions of fixedness in the nature of the way the system works. Now, physical systems are not that way. This is something we imposed on the system by the description. So in our mathematical description, we have an entropic system which is running down toward equilibrium, using up all its energy. But the physical system might not be doing that. So let's ask now the question, does there exist a system which is not subject to the first or second laws of thermodynamics? Well, I say there is, and the human physical economy, that is, human existence regarded as a physical process, is an example of exactly that, and shows that our universe is neg-entropic. Now, I can do that. That's nearly essentially just an exercise in terms of what Lynn presented in his paper on God. Because let's take the following view. Let's look at the Earth, and let's put the Earth in the big box, imagine in space. We can include the sun in it or not, it's not so important. Okay. And now on the surface of the Earth there is a physical process going on, which is the human population and all the activities which human beings are doing on the surface of this planet. And in the what's called the biosphere, which is a relatively thin, spherical, what would you call it? Not a ring, but a shell. Yeah, shell in which all living things on the Earth exist. You have to go down up into the atmosphere, quite high. You find living organisms very high up in the atmosphere, and quite far down to the bottom of the oceans. And in a certain distance, you'll find some even in maybe even under what's called subterranean water, you'll find some bacteria and so forth. You have to go quite, it's a relatively thick region, spherical shell, in which all the living processes are going on. So now we're sitting outside this and looking at this as a physical system. The increasingly dominant part of that system is that which is directly associated with the activity of human beings. And as we watch, imagine that we are godlike beings, that we can watch over a very long period of time, tens of thousands of years, let's say, and we watch this thing, and we see that this process that's going on the Earth is getting more and more intense. That the amount of energy and the amount of activity on the surface of the Earth associated with human society is growing and growing and growing and growing. Well, we can specify this better when we say, if we look across all of human history, that the reason why we have today approximately 6 billion human beings, whereas, let's say 40,000 years ago, the so-called primitive hunting and gathering mode of existence, you could only have had a few, maybe 10 million or a few tens of millions of human beings. The way in which this process has become more and more intense is through scientific revolutions, a whole succession of scientific revolutions. As Lynn calls A, B, C, D, these are, each one corresponds to a state of human knowledge, and you had a scientific revolution going from one to the next, from A to B, B to C, C to D, D to E, and so on. And each one of these states of human knowledge, historically, we could look at the human knowledge 20,000 years ago, 10,000 years ago, 5,000 years ago, at the time of Christ, 100 years after, and so on. Of course, the scientific revolutions didn't come at exactly these dates, but just hypothetically, you have at each era of history, you have a different physics, a different way that human beings were doing things, and a different ideas that the human beings had about the world. Therefore, the activity in this system has different characteristics depending on where I am in this process. After a scientific and technological revolution, the physical process is changing its characteristics of action. Human beings, there's the way human beings, the activity of human beings has suddenly developed new degrees of freedom. Human beings are doing things in a different way than they were before. So you could say in a certain way, it's like what we have in physics, it's like a phase change. Phase change like when you go from ice to water, water to steam. In the same way, this physical system of the human economy is going through a series of phase states. By phase state, I mean a certain way in which the system is interacting. It's geometrical characteristic. Only in the case of water, we have ice, liquid water, and steam. In the case of an economy, it's an unending series of different states of existence. And each succeeding state becomes more intense, has a higher population density. Let's say I'm looking at the healthy part of human existence. So I'm watching this with my microscope from space, and I'm saying, okay, what kind of physical system is this? It is a physical system in which the amount of energy, what I would call energy, is continually increasing, and it is winding itself up. It is becoming more structured. It is an egentropic system. Now, and this has the property, that very crucial one, that each time we go through such a revolution, the resources which are available for going further in this process are growing. So, before we knew about nuclear fission, uranium was not a resource. We'd look at it and say, it's a rock, useless rock. Actually, it was used for coloring false teeth. The history of uranium is really a very fascinating one. It was used by the Romans already, apparently for coloring glass, and was used after the discovery, the formal discovery of uranium as an element. There was a whole industry of coloring glass, beer mugs, and all these kinds of things, and false teeth to give them this nice yellow color, not very nice yellow-green color. And the people who had these beer mugs, the beautiful beer mugs in Germany, which is yellowish-green fluorescence of uranium, and small, were being radiated. And the people had false teeth also, but they were still smiling. It's interesting that these mines there were health spas around these mines. The mine was put into bottles and sold as for health purposes. It contained some amounts of radon and radium basalts. And we now know, well, or we suspect from the phenomenon of hormesis, that actually this relatively low-level radiation does have a positive effect on health. It has now been verified. A slight increase in the background radiation has a positive effect on health. So that's why the people were flocking to these uranium mines long before people knew it was radioactive. That was in the 1890s. Anyway, that's just a sidelight. So before we know we have fission, the uranium is not a resource. After, it's a resource. Before we have fusion energy, seawater is not an energy resource. After we have fusion, from 1 gallon of seawater, we can produce the equivalent of 300 gallons of gasoline. So something that was not a resource before, it's suddenly become a resource. Because the law of interaction, it has changed its meaning to us. Well, what this really means philosophically is, if we think about it, that there is no such thing as a fixed property of any object. No object has any properties in and of itself. Because we can never speak about a property unless we do something to the object, or it does something to us. And depending upon how the object does something to us, or we do to the object, we will see different properties. Well, now somebody's going to come and say, well, but that's just a funny way of talking about the fact that we've learned something more about the fixed universe out there. Right? In fact, the energy that was in the uranium was there all along, only we didn't know about it. Well, okay, so what were the properties of the uranium? Well, if we take all of history into the future, you would have to add all of the properties, so-called properties, through all of the future history of the universe, and say they already existed. Well, they didn't really exist, because what we're talking about here is a process on the Earth which is changing its characteristic. And each time we discover something, this physical process, a real physical process, is changing its characteristic. So it really is changing. And it's, furthermore, it's becoming more and more dominant in the universe. So implicitly, we have to say that our universe also has this characteristic. Because if there's no limit to this, and man is expanding beyond the Earth to the planets, to the galaxy, and so on, therefore more and more of the universe is coming within the span of this process. So finally, So we have here essentially a perpetuum mobile. We have a perpetual motion process. It's not a machine because you never go backwards in this. It's always changing its characteristics. So it's not, you're not getting something for nothing. But it is perpetual motion machine which is winding it's like a clock which is winding itself up all the time. So now if we finally add the observation which Lin describes and talks about in extensively in his paper on God and other papers, that this process of scientific revolution, successive scientific revolutions, there's a law of that. It's not a formal mathematical law, but it is a what's called a higher hypothesis, or above that, the hypothesis of the higher hypothesis, that there is actually a law of scientific discovery, or a method of scientific discovery. Then we have a law of the universe, of this process, and that proves that the universe, by implication, is a negentropic universe. It has a law, but the law is not statable in the form of a logical deductive form such as we have in these textbooks. So that completes, I believe, the proof of the refutation of the first and second law of thermodynamics, and I think that's good news for all of us. And whatever pain it may inflict upon those who have invested a lot of work in mastering the textbook physics, I think the recompense, namely that we're in a negentropic universe which is continuously winding itself up, more than compensates for what we have lost in having to discard certain aspects of what we thought we learned from the textbook. So thanks a lot for your attention. Yeah.
You said in the beginning that the second and third laws, as they were as you express them in relationship to this, this idea of fixed resources and that the resources are running out, are you implying that there is a lawful way that they do work, or that let me see if I can explain the question in another way. And let me add something to the question, maybe it'll help it to develop, which is, what about the statement that these laws work, okay, in physics, that in our machinery, in our technology, it works.
Yeah.
And then in relationship to what you said about this distinction you made.
Okay, that's a good question. What people will say is, you can't attack these laws because our whole technology is going to collapse, because this is how we're calculating things, right? That if you take away all these laws, all of our factories are going to collapse on us, and everything's going to collapse. And I think the point is this: if we just pictorial, this is a picture that I think Lin was using, or I don't know who invented it. We look at these states of human physical economy historically as like concentric geometries. It's almost as if the Earth or the physical economy is growing like this, from a state A to B to C to D. And we have a process which in a certain way is pushing the system through these successive states. Okay, this is the process of human scientific revolutions or scientific discovery. Okay, now, inside each of these things, you can imagine for each state of knowledge, we write a topic. The laws of the universe, edition A, laws of the universe, edition B, corrected, laws of the universe, edition C, right? And in edition B, they say, don't believe anything you read in edition A. Now, there is obviously a certain adequacy of a given state of knowledge from the standpoint of providing a basis for the human existence. Otherwise, it would be irrational, which it's not. At least until relatively recently, at least the majority of engineers and scientists are rational, at least from the standpoint of logical, thought. You can make the following comparison. You have three levels of the human mind. If we take an airplane, one level is the person who created or discovered the airplane and designed the airplane. That's one level of knowledge. The other level of knowledge is the level of knowledge of the pilot who has learned, been trained, how to fly the plane. He didn't discover the plane, he didn't create the plane, but he can operate within that lawfulness, within those rules which he learned and mastered, the plane. That's what we call the first one is called creative reason, the second was called historically understanding or rationality, the deductive sense of rationality as opposed to reason is the higher. And then you have the passenger who finally sitting there suddenly develops a impulsive hatred of pilots and goes into the cockpit and shoots the pilot, causing the plane to crash. This is a low level of animal-like impulses. Okay, so if we look at the intermediate level, this is a level of knowledge adequate to existing within one of these states. The problem is that if we try to exist indefinitely into the future in one of these states, we have confined ourselves to an entropic system. In other words, if we leave out the evolutionary process, we have therefore imprisoned ourselves in a fixed system, and then there are fixed resources, and then it is entropic, right? So that eventually we're going to collapse. So that although the knowledge may be adequate to keeping, so to speak, the machine running, the machine is running down.
Would that be like the status quo?
Yeah, trying to maintain the status quo, trying to maintain the rule, what's happening right now, right? The fanatical commitment to keep the system running even though everybody knows it's falling apart. Because it's not viable as a fixed system. No system is viable as a fixed system. Although we would be crazy, like the guy who killed the pilot, to deny lawfulness and say there is no lawfulness. Obviously, when we go about doing what I was doing, measuring energy with this reference system, we're doing something useful and rational. The same way as when we build a steam engine. When Carnot's analysis of the steam engine was a very useful and necessary activity. He tried to account for what the steam engine was doing to try to increase the efficiency of the heat engine and created something very useful for steam engines and related heat-powered machines. The problem is really a question of developing, getting a certain sense one step further where we have a notion of physics which is not breaking down at the point, what is this problem of Newton, right? He breaks down when you go from the A to the B. What we want is a geometrical formulation of physics, which can bridge the gap. The problem is what happened between Carnot and Kelvin. Newton did vis-a-vis the discoveries that have been made by Kepler. Is that people come along, you have a notion of physics. If you go back to the Renaissance, you have a notion of physics which is this. And it includes both aspects as almost like directions of action. The aspect going this way and the aspect which is operating within a certain mode, but as a stepping stone for going further, where you don't decouple the two, but you say, I have to have my airplane so that I can have my rocket ship, so that I can have my, right? And then somebody comes, like Kelvin, and says, here is Carnot's analysis of the steam engine. Now I'm going to take this and I'm going to make a textbook. And then I'm going to make it into a definition, proof, and so forth. And then I'm going to say this is true for the whole universe. And then I've done something very dangerous, right? So as long as we realize that our state of knowledge is not really true per se, but it is a stepping stone in a process which is ongoing. Then we have gotten it right. And if we train students this way, they won't become idiots, because they'll realize, especially if we train them in the history of science, so that they know a little bit about how this happens. And then everything looks very different, right? Then you don't really lose anything when you go from one stage to another stage, because the previous stage, you know how you got to it. And therefore, you don't throw it away, because it's an ongoing motion. You only throw away the formal features of it to a certain extent. But you throw, the more you formulate it geometrically, the less you throw away in going to the next step. Yeah?
On the idea of mass and mc squared, and I didn't understand, maybe I do. You said the assumption there is that mass is not a constant, and that's a fallacy.
The assumption is that I can take a physical object and I can say once for all, this object has mass x. That seems to be, for us psychologically, this is the question of the axiomatic assumptions of our own thinking. If we don't think about it, we'll fall into the idea that the object actually has a fixed property called its mass. True, in relativity theory we know that if a mass is accelerated, that if an object is accelerated, its apparent mass increases. That's relativity theory tells us that. No, but that's part of, but Einstein takes that into account. Yeah, because Einstein says E equals mc squared, right? And he says, therefore, if I have an object and I accelerate it, I've increased its energy. The velocity of light being constant, according to Einstein, therefore the mass increases. And then you have the formula of the mass equals the rest mass divided by this factor, which tells you that as you increase the velocity, that this apparent mass is actually growing. This is Einstein's relationship, okay? But the point of it is not, the point of it is, as soon as you make a fixed mathematical relationship, you're getting into trouble. Just as before Einstein, there was the law of conservation of mass. This was believed. Mass was conserved under all processes, around 1900. In fact, there were big experiments. Take a chemical reaction, take a candle, burn the candle. All right, if you look at it, it disappears. The people thought first, well, something's happened to the candle, it's disappeared. But if you capture all the gas, which was emitted by the candle in burning, and you take into account the oxygen which disappeared, and you weigh before and after, then it works. The mass before is equal to the mass after, if you include all components of the chemical reaction. But that's not true. We know today that energy was emitted, and therefore the mass at the end will be very slightly less than it was before. Now this difference is so small that it was basically unmeasurable even till today for the case of a candle. Therefore, it was a physical law probably ever devised was the principle of conservation of mass, yet it's false. Okay? Conservation of mass. But that already assumed that you had something called mass, so that this body, so that you could make a law like this. If we make a law like this, then we're assuming we have something called the rest mass. The mass when it's not moving. But somebody could come along and say, well, if we change, if the system changes in a somewhat different way, which we don't know about right now, which we can't define right now, then we'll find its mass will be changed. And we discover that the mass of an object depends on its relationship with the vacuum. Depends on the geometry of space. When the geometry of space is changed, the object or will seem to have a different mass than it had before, even if it's not moving. Although Einstein, in his law, only takes the case of something which is put into motion. So the point is the same. It's all a question of, if we start here with the principle of conservation of mass under all cases, B is Einstein's discovery that the mass is variable according to this law. It increases under motion. C is a discovery that mass increases or decreases under completely different circumstances, until we finally realize there isn't any mass of the object. What we're seeing is the way we're interacting with the system. We're not seeing something about the system. What we see depends on what we're doing. Seeing is an active process. So if we change the geometry of the universe in a certain way, we change the characteristic of action, of our action in the universe, we change the property of everything. That's the way I look at it. Yeah.
This series here, A, B, C,
Yeah.
it represents or can represent the potential population density. So it increases to something that increases. There is this phase change that you mentioned, and that's actually discoverable, and it's a process, that a human can generate over a period of time.
Yeah.
And if that's the case, wouldn't that be, would you never be in a fixed state? Like A wouldn't necessarily be a fixed state because it's a process that's generated.
Right.
And if it's not a fixed state, then you wouldn't be able to measure it. Or can you?
Well, you mean you wouldn't be able to determine what it is, you mean? What the problem?
What it is, or represent it mathematically.
Well, this is what the point is. If we look at A and we look at B, in the case of human existence, okay, from the very fact that we got from A to B, it's obvious that the textbook representation of state A was missing something. Namely, it was missing the process which was already getting us out of A into B. That's exactly the problem of education. Our textbooks don't tell us about how you go from one state of knowledge to the other. They're leaving out the essential point. What is why we say education must be historical. There shouldn't be textbooks, basically, of the present form. One should learn physics from the standpoint of its history. And when you do that in an adequate way by studying at least a selection of the great works of discovery, when the scientists actually made the discovery and report, the best of them actually report their struggle, right? Then we have a completely different notion of the universe than we would if we only have a textbook. So the problem is the very act of formalizing knowledge into this form, axiom, I mean, that's the exaggeration, law, mathematical law, A, B, C, D, E equals MC squared, blah, 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 and then people manipulate with it. The way the mind does that, tries to reduce things to rules, what the mind is doing is it's excluding the mental process, which, this one. Mm-hmm. That's the problem of it's the Kantian problem. Kant described this. Kant was already crippled in this way, because Kant said the process of creativity is incomprehensible. It's magical. It's not subject to a conscious mastery. So you have geniuses who have these intuitions, and the process A to B and so forth come from these geniuses who, zapped. They get zapped by God or something, and then boom, they have the light going on. They have the new idea. Because for him, in his training and his process of personal development, this aspect of his own mind was blocked out, which unfortunately is the case of most people, to a first approximation. Our belief from a Christian standpoint is that every human being has this divine spark in them, but it's been boxed in, so it's an unconscious. They're not conscious of it. The idea is that by this method of education, where one comes into direct contact with creative thinking of great minds, or with great music and these kinds of things, that this is like fertilizer and sunlight for this plant which grows within you of this creative process, which becomes stronger and stronger. You can deliberately develop it. So that's the point. So at each time we can have a formalist, a formal thinking person, and he'll write a textbook. So that is doable. And then we can see the point at which a crucial experiment, the textbook has to be changed. So it's actually a determinate change. It appears as a jump, which we can measure because deductive logical thinking is something which is well defined. It is a real, logical thinking is a real phenomenon. It is also a necessary phenomenon, I think. It's not that I'm saying that we're going to get to a point where you won't have logical thinking, but it's in a certain sense the purpose of logical thinking is to push things to the point where you detect the singularity. You take something like what I was doing in trying to say, okay, well, how do we measure energy? Well, we had this reference system, we did this and this and this and this, and I'd say, okay, well, what's the assumption behind that? So I first have to see how the deductive, more mechanistic procedure is before I can locate the point where it breaks down. So I need this in a certain way, this formal thing, but only as a tool, not as the way my own mind is fixed to work. So it is a real measurable singularity.
So they don't represent fixed states necessarily?
No. This represents, let's say, a formalist view. But this is a way of measuring. Because the reality is change. Right? The reality is never a fixed state. There is no fixed state. Right? Reality is change. But change generates singularities, just as a circle, right? When I fold the circle on itself, I get a diameter. When I fold it again, I get another diameter, and therefore a square. In the same way, change generates singularities. It generates structure. So these are are not really fixed. Same idea of an economy. An economy will have a certain technological level. As you won't find the nuclear reactor prior to the discovery of nuclear energy. It won't be there. So you could classify in a encyclopedia all the different kinds of machines which existed up to a certain point of time. And then there'll be a change and a completely new species will appear. So it is a discontinuity. Just as apparently the evolution of life on the Earth did involve discontinuities. It wasn't a smooth process. Yeah. Yeah, it's a good question. That's a very good question. The difficulty there is, if we take enzymes, which is an interesting case, is, of course, the enzymes don't, the interesting study of them is in vivo, that is, in the living cell. The cell doesn't ever return to its original state. And the enzyme is existing in a certain environment. And this is the most fascinating aspect of biophysics, is how the properties of a molecule are changed implicitly, indefinitely, by changes in the environment within which that molecule is located. So that if we take as the most fascinating and deep question in biology is, what is the nature of the transformation of non-living matter into living matter? If we have a plant, it's growing, and its roots are extracting non-living matter, and this matter is worked up into living tissue. You know, the nitrogen, the phosphorus, and the water, and all this stuff is worked up into this living tissue. So in one sense, from a formal standpoint, we say, well, this is still hydrogen, this is still carbon, right? The chemist will say they're just combined in a different order. You know? But the trouble is, as we know from optical biophysics, when you change the geometry of a molecule, the atoms are physically changed by that, and the nucleus is also physically changed, which is part of the problem of cold fusion. It isn't the same molecule in the new environment than it was before. So the properties of it are changed. Not all. So we find that you can take an enzyme from a cell, extract it from the cell, and we can find that we can catalyze certain processes outside the cell. So certain things are preserved and certain things are not preserved. That's a fascinating... But in principle, life must be similar. Yeah.
Would you say that logic is like a system where reason will be a process then of understanding?
Yeah, you could say, yeah, the quality, let's see, if we take those two modes of thinking, right? The logical mode of thinking is like arranging objects. Like I have a table with different objects, like a puzzle, right? And I put them together. But the objects are fixed, and I combine them in different ways, like a Tinker toy type thing. And in reason, the objects lose this quality of fixedness in our mind, and we think in terms of how things are created. In other words, it's a composition, it's continuing to elaborate itself. So it's in the Parmenides paradox, in Plato's Parmenides, he exactly specifies this change, that from the standpoint of, if we look at the same problem that just appeared, when we say, are there fixed states? If there are, then you could never get from one to the other, right? So then we say a fixed state is a kind of an illusion, because the reality is motion. Therefore, the characteristic of reason is that motion becomes for us the primary reality, and objects only something which is generated and which will be changed in the course of motion. Yeah. In a certain way, yes. Take the following question. Is God fixed or does he change? Okay. Now, you'll find a very fascinating discussion of this in Nicholas of Cuz. Because you can argue for both, right? Because I don't have the theology right on my fingertips now, but if you would say he were fixed, you would imply that he was inferior. He did not have that freedom. Yeah? If you imply that he changes, then you're saying that he wasn't so good because he had to change. Okay? Now what's the problem? Is that so then you're saying, well, then he must be absurd. No. Because he can't be fixed, nor can he change. Because either way he would be not perfect. Yeah. And so what Cuz points out is the problem there is not a problem of God. It's not God's problem. It's a problem in our mind. Yeah. That the attempt to grasp the concept of God as if it were something you could take and fully grasp and put in your pocket, that removes us from God. That's what Cuz called the other. You have, as we would say in leftist jargon, you have alienated yourself. Yeah, you've alienated yourself. The moment you try to make God into an object with some property, you have alienated yourself, and you immediately see that it can't be so. Now, Cuz in the Docta Ignorantia goes through all possible properties. Is God change? Yeah, true either. Yeah. He has every predicate and also the opposite. So, when you arrive at this and you say, well, what could he be then? Right? If the moment we give a name to it, he slipped away, then he must be something which is a law above, of a higher level of that which we could name. Okay? So, and I would refer you to this book on God, that there is an ordering of human thought, the so-called transfinding ordering of human thought, where in the process of motion of the mind, we come closer to God. But not only in that we're moving, only in that we are changing, can we be aware of a higher ordering of change. But not any old change, but a very particular kind of change, a process of perfection. And not in the old process of perfection, a process of perfecting the way we're perfecting ourselves, and so on. So then you get into theology. But these are connected in another way, namely that, as Cuz said, and there's a debate about this, Cuz says that God gave us our body for our own benefit. In other words, because some people think, well, if only we were only pure soul, we'd be closer to God. This is one form of fundamentalism that says the soul is, the body is corrupt and is dirt, right? And what we should free ourselves from the body. Well, there's a certain kernel of truth in that, in a certain, to the extent that we identify ourselves with essentially an animal-like, something, the part of us which is most similar to animals, we drag ourselves down. On the other hand, you're really making God into something, you're saying that God is punishing me by giving me a body and giving me all these abilities. There's something wrong with that. So Coase emphasizes that we find God in what he calls a hunt. He uses all these different kinds of metaphors which he develops. We're hunting for God. We're trying to find out how can we find God. And he says we find God by using what he has given us and by saying that the visible universe, the universe in which we're in, is there in order for us to be able to find God. This is the theological expression of the thing. So we find God by doing this, at least that's necessary aspect of it, by doing this. Because when we're doing this, we are implicitly making the universe, the laws of the universe, to in an ever more adequate way, known to us. Not in the sense of the A, B, C, and D, any of these individuals, but in the law of the progression. So this is very interesting to contrast to the Bogomil notion, the Qatar notion, or I think the Al-Ghazali tradition in Islam, the negative, what I regard as the negative tradition in Islam, as opposed to Ibn Sina and others, Al-Farabi and these sorts of people, that the idea that, in the case of the Bogomils, that they said that the sexual reproduction of man, the reproduction, making children, is evil, is dirty, is a corruption, because you're creating more flesh in a certain way. You're creating more people, and that's corruption, right? And therefore, you should purify yourselves by not engaging in reproduction, not making children. And then they develop all these perversions to how you get pleasure without making children. This is the Bogomils around the 13th century and so on. This was a cult. And it's the same thing in a certain way as as a fanatical belief in the laws of thermodynamics or in logical deductive thinking. Because what you're saying is, to the extent you impose this logical deductive thinking as the only thing, you are confining yourself to, you're saying, I will only think in such a way that I can never create anything. I can never be fruitful. Therefore, there's a direct connection historically between the Bogomils, the buggers as Lynn calls them, and the extreme Aristotelianism, which says there is no creativity, and actually imposes a fanatical form of logical deductive thought as the clean, the pure, the non-fruitful, non-creative in that sense. To be pure, to be abstracted completely from matter. So there are these. So in the end of this, as Lynn has stated, you could say that theology and science are really, in the end effect, the same thing. Yeah, as long as you understand science in the broadest philosophical. The scientist who says God is not interesting to me is insane, because God is the law of the universe. What are you saying? You're a scientist. You're supposed to be finding the law of the universe, and you're not interested in the question of God. It's impossible.
What does the Buddhist say on this?
I don't know. I have never asked a Buddhist. But I mean, the idea would be, one of the important things to say, well, let's now make, as we've been doing in discussions with this kind of approach of Lynn has great advantages, because it provides us a basis for an ecumenical approach. Because, and Coase has it in this dialogue, De Pace Fidei, where he has a dialogue between Islam and Christianity and religions where they agree, but in different, it's like different facets or different ways of arriving at the same thing. So that here we can arrive, and we can finally arrive at saying, okay, well, this is a way of expressing what we're saying, from the standpoint of science, and on that can be a basis for resolving conflicts. Yeah.
Do you think the current state of knowledge that science is in right now, is that a stronger argument for creation, or do you think?
No, I think no state is really, no fixed state is any better than any other one from that standpoint, in and of itself.
This one stands with the current knowledge. Do you think there's more argument for creationism? That's more true?
Oh, you mean in terms of the theory of evolution? No, because I'm convinced that the Darwinian theory of evolution was a fraud from the very beginning. Of a very elementary sort. It's very easy to refute the Darwinian concept of evolution in the following way: that if you, a very simple way, is you say, if you pose the idea that the evolution was caused by random changes, which were selected according to adaptation as those were the best adopted species, the best adapted to the environment, survived. Those that were less well adapted to the environment did not. The problem with that is that the species are changing the environment. Life is changing its environment. And now you have a completely different, Darwin is out of the window, right? If we say, for example, when photosynthesis was invented by the biosphere, yeah, then suddenly an atmosphere which was believed to have been a reducing atmosphere, oxygen was liberated. And the atmosphere we have right now on the Earth was created by the life process for itself. Because an oxygen atmosphere allows a higher energy density of the process. So if we look at evolution from the standpoint of the same parameters we use to measure technology, namely the energy flux density, the intensity of the living process, we see that before man appears, if we follow the fossil record as far as we can, the process had exactly the same characteristics as after man. We continue evolution through technology. Not genetically, man remains genetically the same, but we have an evolution of technology. We have an evolution of ways in which man changes the way he does things. So, and in fact, I know I've worked together with a very excellent French biologist, and he's what's it called? Who's studying who's studying the what's it called? The bones. He works at the Museum of Natural History in Paris. He's not an archaeologist. What is it that you're digging up the bones from? Paleontologist, sorry. But he's also a doctor. He has 2 degrees. He's a paleontologist. He's also a doctor. And now it gets very interesting, because he says if you read books on evolution, usually they just show you the forms of the animals, dinosaur, these various living, strange living beings that were existing at different times. But you only see the outside form. But that's not the important thing. The important thing is the metabolism of the living organism. Because the amount of energy which the living organism can apply in acting on the world limits everything. For example, you can't have a flying being without a certain rather high metabolism. Look at the metabolism of a bird. That's an incredible development to arrive at that rate, metabolic rate, to be able to fly. Right? It requires a whole series of things. And he studied, for example, the question of how you could get to the human brain. That you require the problem of the human brain from a medical, well, let's say if you would want to create such a nervous system, is that the cells of the neurons, the tissue of the brain, requires oxygen, a lot of oxygen. It has a very high metabolism, the brain does, ATP and so on. And when you make the brain as a compact mass, the problem is how do you get the blood to the surface area of the capillaries grows as a function. He has this function of the 4th power or the 5th power of the volume. And then you have to get a certain pressure. So you have a whole series of developments so that you need, in a certain sense, to first have certain metabolic, to arrive at certain metabolic values, to have the kind of a brain that the human being has. So by this, he actually can show that in the evolution, if you look at this instead of the outside forms, and you say, well, the outside forms are determined by the stages of evolution, and he can show that the energy flux density, as the energy per unit volume or whatever, of living beings is increasing on a nice exponential curve, and is therefore ordered. It has exactly this ordering. Now, if and Darwin is then out of the window, because Darwin is saying the same thing. It's the same thing as to say whether creativity is random or not. Do we discover things by searching everything at random? Like the thing of the monkeys, to write a great novel, you have a million monkeys typing at random on the typewriter. That's not the way things are done. Creative discovery is done in a deliberate way by people who are cultured in a certain way, which is this higher hypothesis. So what you're getting here is a very eerie thing, that before man appears, at least from the form of as an embodied entity, you have a biosphere which is creative, which is at least not the individual organisms, but as a development, it has the same characteristics as the creative mind. But the entities within it are not creative yet. Man comes in and he's a creative mind inside the process and outside. So what Cruz says is a very beautiful solution to all of this. He says that the notion of man was created at the beginning by God, and so that the idea of man exists already before man is there, in the mind of God, so to speak. So man already exists as a geometrical characteristic of the universe before he is created or generated in the universe. So that the universe already, implicitly, man is already a necessary consequence of the motion of the universe. He's embedded as a necessary consequence from the beginning. So therefore, there's no contradiction between the idea of a creationism that says man was created by God and evolution. Yeah? Because God creates the universe, which generates man as a necessary consequence of the way God created the universe. Right? So all the contradictions are gone, at least if you don't stick to a literal reading of the Bible in that sense, but a metaphorical reading of the Bible. In a certain sense, on the first day, whatever this means, whatever happened outside of space and time, or the way when space and time was created, the space-time manifold, we would say in physics, the geometry, the curvature of space-time is such that man is embodied within that law. Okay, so this I think solves, at least as an initial solution to the problem. Then we can understand certain things about evolution, which are absolutely mind-boggling, that you see that certain developments are anticipated. It's a big problem with Darwinian evolution that, for example, how do you get... here's a problem of evolution. It is said by Darwin that you have these small variations, and each variation has to give a survival plus, right, an advantage. Well, now you have a problem. If you want to evolve a new organ, such as an eye or a particular form, this organ requires several components to function. Well, yeah, but they have to... Okay, now, if you're evolving toward having this, then when you make a partial step, then you have a non-functional organ, and your investment into that organ is a loss in survivability, which is the same thing you have in the economy. When you're investing in scientific research, that money, that effort is lost to you. It only pays back later on. So that you can't understand how you could get, unless you have something in biological evolution which is similar to an investment in the future, which implies that there's an anticipation of the future. And you find this, according to Dutry, for example, certain fish that develop feet at an earlier period of evolution before the so-called famous first fish got out of the water. But they were already sort of doing, with you know, and I think this is reflected in the fact that living organisms have a certain humorous playfulness, which is also completely contrary to Darwin. They're playful. They don't do things all in order to survive. Like you say, why does a tree have millions of seeds? It doesn't require millions of seeds. Why does it make all these flowers? You can't say why from the standpoint of survivability. It's way too much. So you must say it makes these beautiful flowers because because life does that out of a certain kind of joyfulness. What for us is joyfulness. So anyway, it's a completely different thing of Darwin. So I think Darwin is basically out, and the idea of an evolution is already in Cool's as a Christian idea, as a Christian notion of the states that creation is an ongoing composition. Right. Yeah.
Natural system and put it down as a treaty to counter Darwin or in that time period?
Yeah. The problem was, well, Leibniz already was talking about evolution. He was the head. He was in charge of the mines, the Hartz Mountain mines. With his the mining. In mining, you saw the stratification and the fossils. So already at around 1680 and so forth, Leibniz wrote one of the first books on evolution from the standpoint of his monadology. But I think, as far as I know, there was Lamarck and there was a whole the problem was the debate around evolution from the standpoint of the nuts and bolts of biology occurred after the Enlightenment. And therefore, the whole debate between the Lamarckians and the Darwinians and so forth was all Kantian, right? Because Lamarck and later, what's his name, the Russian guy, the big thing doing. No. The guy that was this big scandal during the Stalinist period of the. No. Was it Russia? Huh? No. No, these are more Cousin. There was the one who believed he'd proven, contrary to Darwin, that changes are inherited. So there's an adaptation. Can't remember there's a big scandal in Soviet Russia. But these were mechanistic notions. You could have a mechanistic notion and say, well, you can have an adaptation where a plant which you grow on a different soil will genetically modify itself, and this will be passed on. But and therefore you have this adaptation lawfully, rather than randomly. In fact, there's a school in Harvard which is claimed now to have discovered exactly that kind of thing. But these are mechanists. This is the behaviorist kind of idea. So you're stuck between one extreme that says it's random, and the other that says it's a machine, which is the same thing as now this chaos theory and the chaos theory is just a further attempt to preserve the mechanism and avoid the notion of the metaphorical law. To understand lawfulness, you have to be able to access the powers of reason. There's ideas which cannot be developed mechanistically. Yeah. Yeah. Yeah.
And you're looking for your collective traits done on that.
Yeah, except that's true, except often it's forgotten that in agriculture, over the course of agriculture, other things are changed. You develop new variety, but you give it more water, or you give it a better soil. So you're not really just so there's another process going on beside it. But it is true that it's only man who, in a certain sense, can evolve as a sovereign entity. before evolution is a question of the entirety of living processes on the Earth in an interacting, this is the so-called ecology. But it was an egentropic ecology. It wasn't an entropic. It wasn't an equilibrium. This is where the whole environmentalist movement is completely off when they say there's a natural equilibrium. What natural equilibrium? There was evolution, which means you're getting further and further away from equilibrium. So who's talking about this natural equilibrium that man is disturbing? Doesn't exist, never existed. The nature moves ever further away from equilibrium. Yeah, so anyway, this is the
Consider the playfulness of animals and the beautifulness of trees. Would you consider those things to be evidence of like the original intent, so to speak?
well, this is the thing. If we think of the laws of the universe not as something written in a textbook, right, but we think of the universe as embodying notions which are of the same order of love. In other words, because most people think dualistically. Dualism. You say, okay, you have this dirty universe, which is working according. This was Descartes. This is the classical dualism, and the amazing thing is you will find that this mentality repeated exactly in your own mind when you're at a certain level of thinking. That since the world around you seems to be entropic or certainly not developing, and yet you have an idea that you're more than just a body. Then you say there's the soul, which is capable of love and all these transcendental things, and is somehow attached to this animal, right? This was Descartes' idea of the dualism of the body and soul, right? Which is an old philosophical problem. So I don't think it's that way. I think that there's that what you find with man, that in a certain sense, you can definitely say that the world and the universe was created for man. You can say that. But not as a Hollywood movie set. But that the law of creation which leads to man embodies those things. So you find that's why children are so interested in animals, because animals are a kind of caricature of it's a humoristic thing, right? There is humor in the living process, what we would call humor. Of course, I study my cat a lot, for example. The cat thing, when you get into this very strange world of cat. But the human mind can develop the capability to, in a certain sense, you'll see the cat and you'll see the cat is very angry, but the cat doesn't know that the cat is angry. He is that way, but he doesn't know it. No? So you can watch this process, and you can also watch a certain, I believe, it's my own belief, is that there's no characteristic of the human being that you won't find it traced of if you look carefully enough in nature. But it's ironical. We see it. It's there, but it wasn't. It was there before, but it wasn't there before. It's the same thing now as you take, for those of us that were longer in the organization, you've often had this experience that you go and you read Leibniz or you read Coase and you say, my God, everything that Lynn is saying is there, right? It's all there. You're making a little mistake. You read Lynn first. And then when you read Lynn, then these people pop out at you. And these ideas these people had pop out at you. But what's actually happened is Leibniz has been changed. He's more lively now than he was before. He's growing because of what's happened afterwards, implicitly. So he's very happy about that. I mean, to the extent that he could be. But these are, you know, these are only, it's only proof that we're where the universe is governed by, in a poetic, when Lynn was saying poetry must supersede mathematics. He means that there are these thought objects. There is a law of the universe which we can access in a metaphorical way. But we can't really, when we make any one of these A, B, C, and D, we're making only a temporary approximation. Yeah. Yeah.
My roommate is taking a class with Carl Sagan. And
With Carl Sagan. Oh, yeah. Uh-huh.
And his latest example of why humans are obviously no better than any other animal is that that chimpanzees make music, or monkeys or some make music, and whatever. So he said, no, they'll be in the jungle and they're wandering around, and they come across a tree and they start banging on it like that.
Yeah.
And they all join in, they have fun, and they have competition, and something like this happens. And we had the argument, but I wondered, that's playfulness. That's what I said, but I wasn't thinking along these lines.
And the problem is, I think, I think the problem is, I wrote a piece a while back called "In Defense of Nature Against Environmentalism," and I developed the whole thesis that whereas these radical environmentalists claim to love nature, in fact they hate nature. If you understand what nature really is, then you realize that they don't like nature. I'll give you an example. As I wrote in this thing, I said, well, you can develop in different ways. One thing is you can say that you don't, you can say we should first get rid of the human being. That's obvious, because the human being is destroying everything. We know that. But let's look at animals. What are they doing? Well, the animal's wasting energy, because the animal, you take the sunlight, which is absorbed by the plants, right? And then the animal's eating all these plants. So if you take a unit of meat, right, there's a tremendous energy loss, right? So that you follow the idea. This is the same argument that is used to say we shouldn't produce meat in agriculture because it's a waste of energy, right? Because you get less pounds of protein per unit solar energy if you have the plants and then have the plants eaten by the animal, right? Therefore, we should get rid of the animals because they're wasting energy. That's true. That's true. They're eating, no, that's very true. The animal is taking these beautiful plants and crunching them up, by brute force. Okay, fine. Now let's start with the plants, The plants are taking this wonderful dirt there, which is just sitting there and just not doing anything, not offending anybody, and the roots are coming out and grabbing these poor atoms and putting them into these unnatural, complicated, what are called megalomaniac molecules with like DNA with these hundreds of thousands of atoms. This is megalomania. This is complexity. This is unnatural. So then finally you get rid of the plants, right? And then you have wind, which is the wind is coming and disturbing the sand. You get rid of the atmosphere. So finally you've got this desert, right? So, and so on and so forth. So you get in. So that's one aspect of it. The other aspect of it is of course, that life is polluting. Do you know any organism which does not produce, there's one opening one place, there's another opening the other place, right? Do you know an animal which is not producing waste? Or a cell, or a bacteria? Only viruses, as far as we know. So we get rid of everything. The virus can't do anything without living cells. And look at the fish. They're polluting, they're pissing in the water, right? Right? So then you say, well, imagine the environmentalist, this was Kraft-Yerke used to say this, the environmentalist who's sitting at the time when you had the so-called, what is called the primeval soup, where there's just some oceans with some little one-celled organisms there floating around. And then suddenly there's some of them come together and form a multicellular system with more than one cells. You say, oh, this is complex. This is centralization, right? They're centralizing, right? And it's got to be decentralized because you have one heart, a centralized power source. So, and then there's the discovery of photosynthesis. And at this point, the environmentalists are screaming at this little, the first algae, which are beginning to do photosynthesis, saying, "You're crazy. You think that growth can go on is unlimited." Right? So at each time in this process, but you have another dimension of it, which is to say that each species has joy in using the capabilities that it has. For example, a bird that can't fly is an unhappy bird. And those that can't fly, I don't know whether chickens could ever fly, but they jump and they do things with their wings, right? So each and a dog runs, and it has joy in running and fulfilling and using what it is given. And if you take a dog and you coop it up, it's going to become vicious and unhappy, right? And the giraffe has this long neck, which is a technology, right? These are all technologies, right? So, and I say, well, what about the human being? The human being is born with the potential for building, creating, growing, so forth. And if you don't allow the human being to exercise that potential, then you create something vicious.
Yeah.
And that's the point now when you get to Carl Sagan. You say that the problem with it is, and the danger of it is, that which is the reason why you need growth, not as a goal in itself, nothing in and of itself which is good in growth. The growth is a way of being. You require an organization of society where the potentiality of the human mind is exercised. Because it is in that exercise of our powers of growing as people that we have joy. Not like any other living being, in a certain way. A higher form of joy, but it's joy nevertheless. So therefore, you have these people who once they get into one of these, once they bottle themselves in this way, they degenerate into something worse than animals. And that's a very dangerous thing. There's nothing more vicious, more destructive than the human being who's not able to exercise their potentiality as a human being. Something more dangerous and more nasty than any animal. So we should watch out for that. Well, unfortunately, we're producing a lot of this problem right now. But I have my hopes. One last question, perhaps.
I just wondered if you could quickly, where you locate someone like Stephen Hawking in this context discussion.
Well, this poor fellow I guess he was educated in Cambridge. I had the misfortune of having been there for several months. And I think he was very damaged. I mean, very damaged by the education that he had. Because this Big Bang is the logical deductive, the Big Bang is exactly the logical deductive idea. That you have the laws of the universe that are created at the beginning, and it just rolls on, right, from the Big Bang on. It's a complete Gnostic, anti-Christian kind of conception, or anti-whatever you want. It's a wild cultism. It's very interesting for people because people like to speculate about black holes and Big Bang and all this. People are fascinated with these things. This whole cosmology. Is the universe expanding? Is it contracting? Are there these black holes? Are there this and that? But and this is an operation of spreading cultist beliefs. Because I believe that none of these questions about the nature of the universe can be approached except for this way. Because you have to think of the universe as a process which is changing its laws, not as something which is, the Big Bang is Newton's idea. You make the watch and wind it up, God wind it up, and it went boop, and then it makes the Big Bang. And, right. So that's the Hawking's thing. It's unfortunate because this is a typical British kind of a problem, that people who are educated in this kind of can be very brilliant in a certain way, very clever, very virtuoso in a mathematical sense, and yet the whole thing is completely deformed. But for cosmological questions, I would propose there's nothing really of value that, as far as I'm concerned, that has been written since Coase and Leibniz on it. Which isn't somehow weird, which is somehow insane. You can go insane thinking about these things if you don't have a grounding in philosophy.
Yeah.
Anyway, thanks for your attention.